In the second approach, let's try to use Quickselect. So this approach is basically the same as the quicksort. For simplicity, we just notice that k's largest element is the same as n minus k's smallest element. Hence, one could implement the k's smallest algorithm for this problem. First, one chooses a pivot which defines position in a sorted array in a linear time. So this could be done with the help of partition algorithm. So to implement partition, one moves along an array, compares each element with a pivot, and move all the elements that's smaller than pivot to the left of the pivot. As an output, we have an array where pivot is on its perfect position in an ascending sorted array. So all elements on the left of the pivot are smaller than pivot, and all elements on the right of the pivot are larger or equal to pivot. Hence, the array is now split into two parts. If that would be a quicksort algorithm, one would proceed recursively to use the quicksort for both parts. That will result in O of n log n time complexity. The subarray is split into two parts of roughly equal size, which reduces the number of comparisons needed to sort the subarray, and we don't need to deal with both parts, since now one knows in which part to search for our n minus k's smallest elements, so that will reduce our average time complexity to O of n time. Our approach used in the select function to find the k's smallest element, which allows us to avoid processing both parts of the partition subarray. So by using the pivot element, we can partition into subarray. Then we can determine which part of the subarray to process based on the index of the pivot element. This approach reduces the average time complexity to O of n, which is much faster than the average time complexity of the quicksort algorithm. So it is possible for us to implement a modified version of the quicksort algorithm to find the k's largest element, only in O of n time complexity, but it requires us a different approach to partitioning the subarray. First, we choose a random pivot, and then we use a partition algorithm to place the pivot into its perfect position. The pivot index is in the sorted array, and we move the smaller element to the left of the pivot, and then we move the larger or equal one to the right of the pivot, and then we compare the pivot index and n minus k to choose the side of the array to proceed recursively. So this algorithm works well even for the array with duplicates. Let's say we have an NAMS array which has elements 3, 2, 3, 1, 2, 4, 5, 5, 6, and k is 4. That means we have to find the fourth largest element in this array. The left boundary is 0, and the length of lambs, which is n, which is 9, and the right boundary is n minus 1, which is 8, and we transfer this problem into length of lambs minus k, which is the 5th smallest element in this array we want to find, and then we import random to find our pivot index, which is index 4. So this is our select function. We import the left, right, and the pivot index into the partition function. So left is 0 and right is 8, and the pivot index is 4, and we all know the pivot is 2, and then we just swap the pivot with right, which is 2 becomes 6 and 6 becomes 2. So this is the first step of our partition function, which is move the pivot to the end. And then we create a new variable store index, which is the same as the left, which is 0, and then we use a for loop for I in the range of left to right. So I move from the left, which is 0, until I move to the right minus 1, which is 7. Now let's start our iteration. We move I from left to right. When I is 0, 3 is greater than pivot. When I is 1, 2 is equal to pivot. When I is 2, 3 is greater than pivot, and when I is 3, 1 is less than pivot. So we try to swap the nums at I and nums at the store index, so we can put the smaller element smaller than pivot into the left, because the left one element is sorted, so we have to increment the sorted index from left to right. And now, let's continue our iteration. We move I from left to right. When I is 4, 6 is greater than pivot. When I is 5, 4 is greater than pivot. When I is 6, 5 is greater than pivot. When I is 7, 5 is greater than pivot. So now I is already equal to right minus 1, so we have to finish. So this is our second step. Move the smaller element smaller than the pivot to the left. In the final step, we should put back our pivot into its original place. Because the pivot was put into the rightmost place, we have to swap the element at the store index and the element at the rightmost. So we just swap it, and in this case, because they are both 2, so the result seems the same. The names at the store index, which is 2, is our partition pivot. It partitions our array into 2 parts of subarray. The left part subarray is less than pivot, and the right part subarray is greater than or equal to pivot. So this is our final step, which is move the pivot to its final original place. And finally, as we all know that the pivot partitions our array into 2 parts, the left part subarray is the names that less than the pivot, and the right part is contain the element that greater than or equal to pivot. So about the relationship between the case smallest and the pivot index, there are 3 scenarios. The first scenario is if the case smallest is equal to the pivot index. In that case, it is already itself, so we just directly return the names at the case smallest. In the second scenario, if case smallest less than pivot index, this time the case smallest must in the left side, so we just search in the left side. We recursively call the select function from the left to the pivot index -1. In the third scenario, if the case smallest is greater than the pivot index, this time we just search the right part because this part of the array is greater than or equal to pivot. And then we just recursively call the select function from the pivot index +1 to the right boundary. From the last partition function, we import the store index as our pivot index, which is 1, and 1 is less than 5. The pivot index is less than case smallest, so it is the third scenario. We recursively call the select function, which has 3 variables: pivot +1, which is 2, and case smallest, which is 5, and the right boundary, which is 8. And then we choose a random pivot index from the left boundary 2 to the right boundary 8. Let's say we choose 5 as our pivot index. And then we just input these 3 arguments in the partition function. So overall, this is our select function. As we just import, the left index is 2, and the pivot index is 5, and the right index is 8, and we swap the pivot 5 with the right boundary 8. So now 4 become 2 and 2 become 4. So this is our first step of partition, which is move the pivot to the end. We create a new variable store index, which is equal to left index, which is 2, and then we try to run a for loop for I in the range of left to right. So I will move from the left, which is 2, until I is right -1, which is 7. So let's say when I is 2, names at 2 is 3, which is less than pivot, which is 4. So we have to swap the names at I and names at store index, both of them pointing at the element 3, so it won't change anything. Then we increment the store index, which is become 3, and we also increment the I, which is also become 3. But the names at 3 is 3, which is less than the pivot, which is 4. So we have to swap the element names at I and names at store index, which is both pointing at the same element 3, so it won't change anything. And then we increment the store index into 4, and we also increment the I into 4, but this time the names at 4 is 6, which is greater than the pivot, so we have to skip it. The store index didn't change, it's still 4, but we have to increment the I into 5. But the names at 5 is 2, which is less than the pivot, so we have to swap the elements names at I and names at store index. So we swap them, 2 becomes 6 and 6 becomes 2. And then we increment the store index into 5 and increment the I into 6. But this time the names at 6 is 5, which is greater than the pivot, so we have to skip it. And then we increment the I into 7. Names at 7 is 5, which is greater than the pivot, but it is our last element, so we have to finish. This is our second step, which is move all of the small elements smaller than pivot to the left side. The store index is 5. We swap the element names at store index and names at right. So we can put back our pivot in the original place. The 4 becomes 6 and 6 becomes 4. So this is our third step, which is move the pivot back to the original place. Number 4 is our pivot. It partitions our array into 2 parts of subarray. The right part is length greater than or equal to 4, and the left part is less than 4. We return the store index from the partition function and input it to the select function, so it becomes our pivot index, and we compare it with the case smallest. Both of them happen to 5, so they are equal, so we have to return the length of the case smallest, which is 4. So this is our select function, and the above is our partition function. In this case, we want to find the third smallest element in the array length, so we use the Quickselect algorithm, which will choose a random element as our pivot element, and we partition the array around it. If the pivot is chosen randomly, then on average, it is likely to be close to the median of the array. So the subarrays on the both sides of the pivot will have roughly equal size. So this will result in the balanced partitioning of the array, which is O of n time in average case. Because in the average case, the partitioning operation divides the input array into 2 subarrays of equal size at each step. So in this case, the time complexity of the Quickselect algorithm is O of n time. In this case, we want to find the first smallest element in the array length, so we use the Quickselect algorithm. It may repeatedly choose the first element of the array as our pivot, so which result in the subarray with n-1 element and having all of the elements, and another subarray with only 1 element be empty. So this results in n recursive call and n partitioning operation, which take n multiplied by n, which result in a worst time complexity of O of n squared. So this occurs when the partitioning operation consistently chooses a bad pivot. So in this case, the partitioning operation divides the input array into 2 subarrays, one with n-1 element and another one with only 1 element. So if this happened at every recursive call n times, then it is the worst case. However, the worst case scenario is very rare in practice. It occurs only when the input array is already sorted or nearly sorted. So in most cases, the Quickselect algorithm will only run in average, which is O of n time complexity. We calculate the index of the case largest element in the input array length, and then using the select function to return that element. So the select function will find the case smallest element in the input subarray. So if we try to find the case largest element in the input array, we can pass the length of length minus k as the case smallest parameter to the select function. So this is because the case largest element in the array is equivalent to the n minus k smallest element in this array. Well, n is the length of the array, right? For example, if the length of the array is n is 6, we want to find the second largest element, then we use the select function, so we can find the 6 minus 2, which is 4th smallest element, which is the same as finding the second largest element. In the select function, we have found the case smallest element within the subarray defined by the indices left and right, and the case smallest parameter, which represent the index of the case smallest element within the subarray. We assign a random integer pivot index variable between the left and the right indices of the subarray. This is done to avoid worst case time complexity when the input array is already sorted or almost sorted. So if we always choose the first or the last element of the subarray as our pivot element, then the partition algorithm maybe not split the subarray into 2 parts of roughly equal size, which result in the worst case time complexity. By choosing a random pivot element, we can ensure that the partition algorithm is less likely to split the subarray into unbalanced parts, so the average time complexity of this algorithm is closer to the O of n instead of O of n squared. We call partition function, which takes the input subarray defined by the indices left and right and the pivot index, and after partitioning, the partition function will return the position of the pivot element, which is the index of the first element in the right subarray. It is the index of the store index. In the partition function, we select a pivot element from the input array names, which is at the pivot index position. The pivot element is used to partition the subarray into two parts. The left side contains all of the elements that are smaller than the pivot, and the right side contains all of the elements that are larger than the pivot. The pivot index can be any index within the subarray. It is typically chosen randomly to ensure that the partitioning is done in an average case time complexity of OFN. The pivot variable holds the value of the pivot element, which will be used to compare with other elements in the subarray during the partitioning process. And then we move the pivot element to the end of the subarray just by swapping it with the element at the right index. So this is done so that our pivot element doesn't get in the way of the partitioning algorithm. Just by moving the pivot element to the end, we can start partitioning the subarray from the left side and move all of the smaller element to the left side of the subarray without interfering with the pivot element. And then we move all of the small element to the left of the subarray. We start a store index variable, initialize it to the left, which represents a position where we swap the pivot element to its final position. After removing all of the small element to the left, we then use a for loop to iterate through the subarray from left to right. For each element in the subarray, we compare it with the pivot element. If the element is smaller than the pivot element, we just swap it with the element at the store index position and increment the store index variable. So this moves the element to the left side of the subarray to ensure that all of the small elements are on the left side of the pivot. At the end of this loop, all of the small elements are on the left side of the pivot, and the store index variable points to the position where the pivot element should be placed. And then we move the pivot element to its final position. We do this by swapping the pivot element, which is currently at the right index, with the element at the store index position. So this moves the pivot element to the position where all of the smallest elements are on its left side and all of the larger elements are on its right side. At this point, the subarray is partitioned into two parts. The left side contains all of the elements that are smaller than the pivot, and the right side contains all of the elements that are larger than the pivot. The store index variable keeps track of the position in the subarray where next element smaller than pivot should be placed. So just by swapping the pivot element with the element at the store index, we could move the pivot element to its correct position in the subarray, where all of the elements to the left are smaller than the pivot and all of the elements to the right are larger than the pivot. And after partitioning, the partition function then returns the store index, which is the index of the pivot element in the subarray. So this index will then be used by the select function to determine which subarray to search for the k smallest element. After we partition in the subarray, we obtain the position of the pivot element, and we compare the k smallest parameter with the pivot index to determine if the k smallest element is in the left or the right of the subarray. If the k smallest index is equal to the pivot index, then we have found the k smallest element and we can directly return it. And if the k smallest index is less than the pivot index, then the k smallest element must be within the left subarray. We can recursively call the select function on the left subarray with the same value of the k smallest. If the k smallest index is greater than the pivot index, then the k smallest element must be within the right subarray. Then we can just recursively call the select function on the right subarray. By comparing the k smallest index with the pivot index, we can narrow down the search space for the k smallest element to reduce the number of comparisons we needed to find it. So in finding the k smallest element, this is what makes the select function more efficient than the other algorithms like quicksort. If the subarray defined by the indices left and right contains only one element, then we return that element. This is the base case of the recursion. If the subarray has only one element, we don't need to partition the subarray any further, so we can just simply return that element.